Professor, I think everyone. Okay.
Okay, very good.
Uh,
Oh,
I
just
think
Pelus, I
Pelus
think.
is, yeah.
Oh,
what? Sorry.
one student is yet to connect.
Okay. Now I think it's okay, right? Hello? I think now it's okay. We are 11, so it should be, no?
We are waiting
Yes.
for Pelus. Oh, Pelus is here.
We can start.
Okay, we can.
Okay, let's start. And so I changed my mind. So I will continue to discuss about time-dependent perturbation theory because we need to fix a few concepts. And then Thursday, we will do extra exercises on time-independent perturbation theory. So let me stress once more, what is the aim of time-dependent perturbation theory? So you have an Hamiltonian H, which is given by H0 plus lambda V of t. So now the perturbation, this is the perturbation. Is time dependent. Okay. So the goal is not anymore, since this is time dependent, the goal is not anymore to determine the shift in the eigenstates or eigenvalue, but the goal is to find the evolution of psi of t induced by, so the dynamics of the system, so meaning the dependence on time of psi of t induced by the Hamiltonian H. What do we know is the dynamics, so all the properties of H0. So what we want to compute are an approximate solution for, there is a question, yeah, just a moment. Jonas, please, okay. We would like to find an approximate relation of an approximate expression of psi of t. Okay, so I remind you the basic steps where, so first of all, we found a convenient representation, a convenient basis. Okay, and the basis over which to construct the perturbation theory was to consider this, the basis of the eigenstate of H0. So it's minus I E. And we just wrote the psi of t in this form, psi of t as in this form, which is still very generic. The only thing we need to know is now to find a perturbative expression for C, for the Cn. Okay, so the goal is to find the Cn. This we don't know, and we will determine by perturbation theory. So if you remember, then we did what we did was, okay, let's try the following. So we just do, we just write Cn as C0 of n plus lambda C1 of n of t plus da da da, okay? Plus lambda to the power q cq of n of t, and so on and so forth. And the nice thing about this expansion that we could write a chain of equation in which it was something like this. So some equation was, the first equation was dc0 of n dt was equal to 0. And then we had that the Cn of q dt, okay, I was related, so to C q minus 1, okay? So we had this chain of equations. So you just you start solving this, then you just go to the next one, you go to the next one, and you decide to stop at some point, okay? So something very important that we learned yesterday was the fact that if you apply, so if you start, for instance, from in a given eigenstate of H0, so we just said, let's start from at time 0 in a given eigenstate, say phi 0 of I. If the system is put there, then there is a possibility to induce transition to to different states, okay? And the first thing we did was to, actually the only thing I think that we did was to show how to compute the probability of transition from one eigenstate phi 0 of I to another eigenstate phi m of I in perturbation theory, right? Now, today, we are going to discuss a chapter which is very important in perturbation theory, which has to do with periodic perturbations, okay? So this is where we stopped yesterday and where we start. Okay, so periodic perturbation. So essentially what we want to do is to consider a situation where the perturbation is such that V of t plus capital T is V of t, okay? Actually, for simplicity, we will assume that V of t is just equal to some operator V times cosine of omega t, okay? Now, let's try to apply the formulas that we got yesterday for the generic for the generic perturbation to the present case, okay? So for simplicity, so I mean, the lambda is included here, okay? We can just write it here, lambda V, but it's really not really important, okay? So if you remember, yesterday we saw that if we want to know in first order the probability to go from the state I to the state N as a function of time to the first order in perturbation theory, this is nothing else that lambda times C1 N of t, okay? And what we saw yesterday was that this C of N of t is nothing else than the integral of, let's say, between t0 and t of dt prime, and then you have V n I of t e to the I omega n I t prime modulus squared, okay? So this omega ni, I just remind you, is just the energy difference, okay? It's just E0 of n minus E I 0, okay? This is essentially the level, the difference in the level, in the energy levels, okay? So no news in terms of new formulas. The only thing I want to do is just to compute this expression for the case of perturbation theory. Okay, so the only thing we need to do is just to write explicitly this expression for the case of periodic perturbation. Okay, so I just, for simplicity, take T0 equals 0, and basically I just include lambda V in V. Okay, so V lambda is included in the matrix element of V. So first of all, you see that essentially, in order to calculate this integral, then we have to compute the matrix element and then do the time integral. The time integral. Now the matrix element will be V. Sorry, I just made a mistake. It's just VNI, which is, I'll just remind you, is Φ0 n V. Okay, Φ0 of I. Okay, this is the matrix element, and then I have to compute the integral between 0, we said that we start from 0, and t of dt prime cosine of omega t e to the I omega n I t prime prime. Okay, and then do the modulo squared. Now already here you see that what is really important, I mean, this integral will be very strongly influenced by the relation of the applied frequency, of the frequency of the applied perturbation with the level separation. Okay, basically you have to integrate over periodic function, I mean trigonometric function, and therefore this integral will be very much different on how the frequency omega matches the omega n I. In order to do this integral, this is something very simple. What you do is just to write down the cosine of omega t prime as 1/2 e to the I omega t prime plus e to the minus omega t prime. Okay, so then the integral is very simple, and the result is the following. Okay, so I just write.
Sorry, Professor.
Yes.
Okay, I wanted the page.
Yes. Yeah.
Okay.
Do you want to see it, or you need the?
I wanted to copy something before.
Okay. Okay.
Okay, can go.
Okay. So look, now the integral is simple. Okay, it's just you have to do the integral between of an exponential. So this is something simple. So if you put everything together, the result that you get is the following. So I just write, and then you tell me if there is something that you need to discuss. So the probability to go, so if you start in the state I, the probability to go to the state n will be equal to V n I modulo square divided by 4, okay, times, and then you have two terms, 1 minus e to the I omega n I plus omega t divided by omega n I plus omega. And you have also the term omega ni minus omega. And then you have 1 minus e to the minus to the I, sorry, not to the minus I, omega ni minus omega t modulo squared. Okay, so the fourth comes from the cosine. The cosine is 1/2 of the sum of exponential, and then you have to do this, the integral of the two terms. Okay, and you just get this. Okay. Hello, is it okay?
Yes, yes.
Okay, good. So let's see how these two terms, I mean, the relative importance of these two terms. And for simplicity, we just assume that omega ni is larger than, is positive. I mean, this is just for discussion. It's not really important. If omega ni is negative, things change. Now, just look at these two terms. Terms A, sorry, I just call it differently. I just call it. There are several names. I don't want to confuse, so let's call it A and B, okay? So A and B.
Professor, the VNI square, the VNI module squared, where did you get it from? I mean,
so you see, the V has some operators times the cosine. Okay, the operator will give you some matrix element, which I call VNI, and then I have to do an integral over the time.
Oh, so but I mean the integral should include VNI, right? So
suppose the following. So I call it V of t. Let's do this way, and I call it this as V0, which is something. It's an operator. It's time independent times cosine omega t. So
okay,
this is just V0.
Yeah. And
so you see, this is time independent, so you can take it out from the integral. Okay.
Okay.
So let me do an example. Let's see if it works. So just imagine that you have an harmonic oscillator, okay, which is omega 0, okay, n plus 1/2, and then you have lambda v is a plus a dagger, okay, times cosine of omega t. Okay, so you see that the let's say I just put some coefficient lambda. Okay, so you see that the perturbation has some operator part, which is time independent, which is important in determining what transitions are allowed and which transitions are not allowed. Okay, so for instance, suppose that you start from 0, then you have to compute, and you want to know what is the probability that from 0 you end up in the state 1 as a function of time, okay, by means of this perturbation. Then what you have to compute is 1 a plus a dagger 0 modulus square times the integral between 0 and t of dt prime cosine of omega t e to the I omega 0 t, where omega 0 is the difference between the first the ground state and the first excited state. Okay? Hello?
Yes, yes.
So for instance, if you would have computed, if I with the same approximate, if the same perturbation, I ask you what is the transition to go from 0 to 2 in first order, then you would have to compute 2a plus a dagger 0 times the integral, but this is 0. Okay, so in first order perturbation theory, the only allowed transition are between 0 and 1 and not between 0 and 2.
So you put the position operator as
for example, as a perturbation, yes.
oh.
Is this clear or not? Should I repeat it? So tell me, should I repeat it or not?
Wait, don't erase.
Oh, it's too late. I erase it, so let me do it again. Okay. Okay, sorry, I just write it here. So let's consider a perturbation, okay? Perturbation which is time dependent, I call it V of t. This V of t, so V of t is an operator which has some explicit time dependence, okay? So I'm considering the case in which V of t is some operator V0 and the time dependence is just periodic. It does not matter, it can be whatever, okay? Is this okay or not? Do you want an explicit example? So let me do an explicit example. So suppose that you have an harmonic oscillator. So I have p squared over 2m plus 1/2 m omega 0 square. And then I take this x minus x0 of t. Okay. Or no, this is too simple. So let me, I just write it in a different way. So I just take this x squared, and then I just put plus lambda x over L times cosine of omega t. Okay, so this is H0, is the Hamiltonian of the harmonic oscillator. And then I'm just putting a force which is coupled to, or a potential which is coupled to the position, but the coupling is changing with time in a periodic fashion. Okay.
Yes.
Now, in the expression that I have to compute there, I have to compute some matrix element of this object between the eigenstate. So I just call the eigenstate n and n prime, the eigenstate of the harmonic oscillator, and then I have to compute L x over L cosine of omega t. Then I have to take the square, and then I have to do some integral. Okay. Now, before doing the integral and take the square, I just noticed that cosine is a function, lambda is a function, L is, lambda is a number, L is a number. So it's a C number, so I can take it out from the matrix element. So this is equal to the integral of dt prime of the exponential, everything, I mean. So I take it out, and then I get lambda, I take it out and I get n x n prime modulus square. Then I get lambda just a moment. This should go out. Okay, it's just out. Lambda over L times cosine of omega t times the exponential of omega n prime, and then the square. Okay, so you see that this term here does not depend on time. So this is nothing else that v n prime squared, which is this term here, Okay, or not?
Wait, Professor?
Yes.
Why you write the time independent term with square? I mean, since it's inside the square too. It's a bit confusing.
Okay, so let me do it again.
I mean,
no, just a moment. Let's do it step by step. Okay, let me here. So is it okay, this expression here, this one? Is this one okay?
Yes.
Okay. So I have to compute the VNI of t, okay? Which means that I have to compute phi 0 of n, V0 cosine of omega t, phi 0 of I. Okay? Say yes or no.
yes, yes.
So this is equal. So you see that cosine can get out of the matrix element. So this I can just write as phi 0 of n V0 phi 0 of I, okay, times cosine of omega n I of t. Okay? Okay?
Yes.
So, and what I'm saying is that I call this Vni, Vni cosine of omega t. Then I just take this expression and I put it here and I just do the integral. And then I take the square. Is this clear? So let's do it. Okay.
Can you go back to?
Yes, just a moment. I just erase this. Yes. So I just let me rewrite on the other page, okay?
Okay, it's done.
So,
Thank you.
okay. So I just write I have to do this integral between 0 and t of dt prime of v and I cosine of omega t prime e to the I omega and I t prime, and then take the absolutes. Okay. So this is equal to, so this does not depend on time. So I can just write it here. V and I, the integral between 0 and t of dt prime cosine of omega t prime e to the I omega and I t prime. Right? Now, this integral, this one, you can do it, is just equal to v and I, and then I have 1/2. Okay, so just put the 1/2 here. The integral over g and t of dt prime e to the I omega plus omega n I t prime plus e to the I minus omega plus I omega n I t prime modulus squared. Okay, so this integral is nothing else than this term here. This integral is nothing else than this time here, and then I have to take the modulus squared. So this is equal to v n I modulus squared over 4, and then I have the modulus squared of 1 minus e to the I omega plus omega n I t divided by omega n I plus omega plus 1 minus e to the I omega n I minus omega t omega n I minus omega modulus squared. Okay.
Actually, this part is clear already, and I was
Oh.
asking about another part. So
Sorry, then I did not understand what you were asking.
I mean the part where you are trying to solve the harmonic oscillator.
So, just a moment. Is this clear? Yes. Tell me. Is
Yes,
this is clear?
this is clear.
Oh, very good. Sorry, I did not. Then, okay. So this I erase. So what was the example I gave? Was not clear?
As a perturbation with the position operator.
Okay.
Yeah.
So yeah.
Dependent on time.
So I had H0 was omega 0 n plus 1/2, and the perturbation was lambda x over L cosine of omega t, right? What was it? This one I don't remember. I just wrote it by.
Yes, it's similar. Yeah.
So it's similar. I don't remember what I wrote. Okay. Okay. So x over L is just equal to lambda over square root of 2 a plus a dagger times cosine of omega t. So what was the equation? So I think what I said was that if in this case I have to compute the V and I, So if the initial state is 0, then the only matrix elements which are different from 0 are those for which Vn, comma 0 is equal to delta n1, because these are just n apart from the coefficients. Okay, let's put it proportional. N a plus a dagger 0 is equal to delta n1. What was the question then?
Yeah, why basically I don't remember, I don't get why it's
What
only the 0 to 1 transition that can happen, and 0 to 2 cannot happen.
Yeah,
I think you
apply so this one, when you apply a single a, so let's say a dagger applied to 0 is what?
Is 1.
Okay, so if you apply a creation operator to the 0 state, you go to the state 1. Okay,
Yes.
if you apply a to 0, you get 0, you annihilate the state.
Yes.
So this will not contribute. So you have a dagger to 0 is 1. So this becomes n1.
Okay, I get it now.
Okay,
Mhm.
so that's why you get. So to summarize, sorry. To summarize, so this, the terms Vn, this one will give you the kind of eventual selection rules. It tells you that in first order in perturbation theory, what matrix element, I mean, not all the transitions are allowed. So there will be certain transitions that are allowed and certain transitions that are not possible. While these other terms will tell you kind of how big is the probability or how small the probability of transition. Let's see these two terms separately. Now, as I said, let's take omega n I to be positive, just as an example. You can do exactly the same discussion with omega n I negative. Now, if omega is close to omega n I, can you tell me if there is one term which is more important than the other? It's not equal, but saying it's close. It's just
the first term, the A term will be important.
so you say A or B. Well, there is well, but then if you see A, the denominator will be just twice omega n I, while the denominator of this will tend to 0.
Yeah, so B is much bigger.
B is much bigger. So you see, it's like having, so let's say, if you write this as omega n plus delta omega, okay, let's do this way. Oops, sorry, used to be. So let's take omega equal to omega n I plus just delta omega, which is small. Then this term will go like 1 over 2 omega n I plus delta omega, while this term will go 1 over delta omega. right? So this term, when you approach the level separation, this term will tend to diverge. Be careful because about divergence, because still there are this perturbation theory, while this term is bound. Okay. So when you take a periodic perturbation that is, which has a frequency which is close to kind of transition frequency, then basically out of this cosine, this periodic modulation, let's say people, I mean, a way to say is that there is a rotating contribution and counter rotating. It's like having, so this leads to a resonance, while this does not lead to any resonance. So, do you see it, or should I repeat it again?
What did you just say? The contribution.
So, when
I don't get the resonance part.
okay, so let me ask the following: what is a resonance? So this is something
High frequency.
Huh?
Resonance is the frequency in which you bring all vibration the same in the system. The system is vibrating. Maybe if we go back to classical physics.
Yeah, like in classical physics. So what is a resonance phenomenon?
It's like you bring the system into its natural frequency.
And what happen if you bring you just perturb the system with a frequency which is close to the natural frequency?
It's like the phenomena of blowing up, because the frequency will
blowing
pick up.
Up or what?
On the frequency.
No, blowing up. So that in classical mechanics, you have the amplitude of the oscillator becomes large.
Yeah, becomes large. Amplitudes become large. Yes.
Okay. So essentially, it's not that you're applying a strong forces, a strong potential, but if you choose the frequency, which is the right one, then the amplitude of the force, I mean, the amplitude of the reaction of the system to an external force will be much larger, because it's a fine tuning. You choose to match the external frequency with the natural frequency, right? Now, let's see if you see something similar here. Now, what is the natural frequency of the system?
I want to verify.
No, you have to speak louder because I do not.
I want to verify. For me, I think resonance is when we have a external potential or external force or something.
You should speak. Sorry, I cannot hear you. You should speak louder, or put the microphone high. I don't hear.
Can you hear me now?
No. So I just hear the voice, but I cannot resolve the words.
I can hear her voice. So.
Okay. So, but you are young. I'm old. So you should speak.
Can you hear me now?
Now it's okay. Yes.
Okay. For me, I think that the resonance happen when we apply an external force with a frequency that close or equal to the frequency of the system. So we have the resonance phenomena.
And what does it mean that the resonance phenomenon? What does it mean? So
it means that when we apply an external force, and then when the frequency of the external force is equal or close to the internal frequency, and then the amplitude of the oscillation blows off.
Very good. Yes.
But I don't really understand. My colleagues, my friends said that you bring the frequency of the system into its nature. I just don't understand.
The frequency. No. They said it's you just choose the frequency of the external force close to the natural frequency.
Oh,
yes. What they said.
Yeah.
which is
okay.
exactly what you said.
Okay, yeah. I
Okay,
just
sorry.
maybe misunderstand my friends.
No, I think just a moment. Sorry. Just a moment. Share screen. Start. Okay, now it's okay again. Good. So this is the resonance. So the resonance that you know is the fact that, I mean, this is the picture that you saw, you know, you have in mind, right? So that you get something like this. The amplitude as a function of omega minus omega 0, right? This is the amplitudes of the oscillator. So this means the following, that if you force the system with a frequency which is close to the natural frequency, then the response of the system will be highly enhanced, right? Hello?
Yes.
Yes, yes.
Okay. So let's see if you see something similar here. Now, here the situation is the following. We have, I mean, we are doing in perturbation theory, but it's not really important, I mean, for the discussion. So you're applying to the system an external potential, okay, which is this one. And this external potential is time dependent, and in particular is periodic, okay, or this one, right?
Oh, I'm sorry for interruption, but I just realized where's Pooja.
What?
Pooja, I see one of my friends not here. I think she was there.
What do you mean, one of my friends? I don't understand.
I mean,
We miss one
classmates.
of our colleagues.
Ah, okay, sorry.
We send her.
But was he present before, or he was?
I just
Yes, she
realized.
was present. I think that there might be instabilities with her connection because she connects and leaves, connects and leaves. But yes.
Ah, okay, but is she in the guest house or?
Yes, she's in Adratiko guest house. Yes.
I can try calling her on her extension and see what's on.
Okay, so I'll just wait. So okay, so
Just a minute.
okay, I just wait. Okay, you tell me when I should start again.
Okay, she says the connection is lost. She's just trying to reconnect.
Okay,
Hmm.
so tell me when to restart. But when do you just tell me? Is there anybody else in the guest house at the present, or?
Yes, yes.
Yeah, I mean,
Okay,
the
but
guest
for
house.
you it's okay.
Yes.
Yeah,
Okay, but do you use sorry? Do you use wireless, or you have cable?
it's cable, so it shouldn't be I mean,
Okay,
shouldn't be
because
an
cable should be more stable.
yeah.
Yes, the cable is stable. So I think it's the wireless that is usually unstable. Yeah, it's unstable, right?
But in fact, for example, Haga room, other friends, like the cable is not stable. It depends on the room, actually.
Okay, but is this a new thing, or because if it's recurrent, then you
Yeah,
should.
it's actually recurrent.
Okay, but did you inform the ICTS?
I think we already informed it when in the meeting with the director, but I don't
No,
know.
but just contact, okay. So either you contact directly ICTS, or you just contact directly Professor Kiselev. Just
Oh,
tell Professor Kiselev, and Kiselev will inform the ICTS.
oh,
Let's say which room has problems, or okay.
yeah, yeah, okay.
She's not reconnecting, right?
No.
As I guess we can continue.
Yeah, I
Maybe
think maybe
yeah.
there is
Let's do the
Watch
following.
the recording.
Just
Yes.
yeah, or you tell her that she may contact me, and I can redo this part of the lecture. Okay.
Okay.
What's
Oh,
her
she's
name?
joined.
is here now.
Okay,
Is-
now it's okay.
Yeah.
Ah,
Oh, so we can continue, Professor.
Okay. So we now we know what is a resonance effect. Then I really would like to show you that there is a connection to the resonance also here. So we have a system, and we are applying a time periodic perturbation with this cosine, right? So it's a periodic external potential that we are applying. Now we have two frequencies. One, which is the external frequency omega, and the another one, which is the natural frequency. Because if I mean, the system has many levels. So it's not like the harmonic oscillator that there is only one frequency, only one natural frequency. Okay, so they may be different situations. But if you take a pair of levels and you choose a frequency which is close to that particular difference, then we saw mathematically that this term is much smaller than this other. So this is the dominant. B is much more important. So let's put it this way. Okay. So then what happens? If you tune the external frequency close to the natural frequency, then the probability of transition is greatly enhanced. So also here you have that the system responds to an external perturbation in a very sensitive way, depending on the fact that the applied frequency is getting closer and closer to the natural frequency. This is a resonance phenomenon. Okay, the system is resonating with external frequency when the external frequency is close to its natural frequency. Right?
yes.
Okay. But this is something you know. I mean, now we are going in various details in the discussion, but this is something, I mean, you already know. You know that in order to have, I mean, you have absorption of the external radiation, then the frequency of external radiation should match the energy separation between these two levels, apart from selection rules. If there is no such a matching in frequency, the atom cannot absorb. They are a discrete spectrum. And this has been seen by the fact that light, so only certain frequencies can be absorbed by an atom, because the atom should jump from one level to another, does not have a continuous way in get absorbing the external radiation, right? You know this. Huh? Okay.
Yes.
So if we drop this term, then we can just rewrite this probability in a more compact way. And if you are close to the resonance, we just put resonance to just to indicate that only one term has been considered. This is approximately equal to V n I square over 4. Remember that we always put h bar to 1. So if you want to include in right dimension, then you have to put back the h bar sine square of omega n I minus omega over t over 2, okay, divided by omega n I minus omega over 2 squared. Okay.
Professor,
Yes,
let me ask, maybe this is a useless question.
there are no uses.
When we say th bar to 1, is it having any physical meaning or it is just for convenience of calculation?
No, it's just it's for convenience.
Okay.
Okay. So I mean, h bar to 1 means that you're just fixing the units. Okay. So for instance, if you fix h bar to 1, so the energy has the dimension of a frequency. Okay.
Okay.
But it's a choice. Okay. So if you want to put back h bar here, you should put it here. Okay. Now, so you see that this expression will diverge when sorry, there is a here, so it's not divided, it's like this. Okay. So just to make it here, divided by 2. So when does this expression diverge? It does diverge when omega going to omega ni, which is something we know, we already saw at the beginning. But so this is not possible because we know that this is perturbed. So first of all, a probability cannot become larger than 1. Okay, this is important. Moreover, we know that in perturbation theory, this correction should be small. Okay, so this is important. You should keep this in mind. So one should determine when this expression is valid or no. So if you consider finite time, then you see that this sine squared divided by omega is a function of how do you say, of the frequency difference is something which is something like this. It's something like something, so it's a function of like this. So this is a function which has a width of the order of plus minus 2 pi over 2 pi over time. Okay. So it is important that you should agree on the validity of this expression such that perturbation theory is valid. Then you see that if you are on resonance, if t becomes too small, then this probability is not anymore a good choice. So for instance, just for simplicity, just take omega equal, just take the resonance condition. Okay, so at the resonance condition, then this expression is nothing else than VNI square over 4h bar square, and then you have omega ni minus omega over 2 squared times t squared divided by omega ni minus omega squared. Okay, so you see that this scales like VNI squared over 4h bar square times t squared. As long as, I mean, in order for perturbation theory to be valid, then this should be much smaller than 1. So this means that the time should be much smaller than h bar over v and I in modulus. Okay, so this fix a limit on the time. But there is more to that. In order for the resonance condition should be to be valid, and this you can verify. So in order for this term to be much more important than this term, it turns out that the time should be larger than 2 pi over omega n I. So if time is too short, then the resonance condition does not work. So in order, so let me say the following. This means that in order for the resonance condition to be important, then the system should resolve the fact that you have a given frequency. Otherwise, this does not work. But this, if you put the two expressions all together, then you find that more or less the time is for which perturbation theory works should be in between this and 2 pi over omega, or more or less omega ni, because we said that omega and omega ni are more or less the same. So this is somewhat a way in which one can estimate where perturbation theory works. Now, what does it mean? It means that if you want to consider a frequency which is close to the resonance frequency, and you want to consider two very large times or two small times, the expression that we got is not valid. Okay? But let's elaborate a little more on this. And the next thing I would like to discuss is something which goes under the name of Fermi golden rule. Did you hear about this or not?
Yes.
Do you know already what is it, or should I repeat it, or can I skip it? Tell me.
No, don't skip this, please. Thanks.
Okay, so let's see what does it mean. So Fermi golden rule is an expression which allows to determine the probability of transition from one state to another per unit time. Okay, so it's Fermi golden rule allows to determine the transition rate. Transition rate is nothing else than probability to have a transition per unit time. Okay, now in order to determine, I mean, there are several ways to determine a Fermi golden rule. We just follow this, the approach that we are using now, perturbation theory. Okay, this with this same formalism. So since I told you that when a frequency is close to the resonance frequency, then there is one term, the resonant term, which is much more important than non-resonant. Then we just forget, for simplicity, this term here, which means another way to say it is that we just assume that H is just given by H0 plus V times e to the minus I omega t. So we are just dropping a similar terms like V to the I omega t. This term we are just dropping, okay? So we just take a symbol exponential. If you just take exponential, so you just consider, so it's like having if you plot this I omega or minus I omega on the complex plane, means that you are just following a point going either clockwise or counterclockwise. So if you use a symbol exponential, you just choose one specific direction. If you put the cosine, you're just putting both the rotating and counter-rotating term. Okay, so we forget about this term here, which, as I explained before, is justified if we consider the system with a perturbation which is close to the resonance. Now, let me write again the probability that we just saw previously. So the probability to be close to resonance. So in the condition of close to resonance, the probability to go from the state I to the state N as a function of t is just more or less equal to V n I square divided by H bar. And then we just add things in order to write it in this way. Okay, so I just first write it, and then you will see that this is exactly omega n I minus omega t over 2, and then I have omega n I minus omega divided by 2 squared. Okay, so I just add, and so not add, so put in the numerator and this denominator this pi t and pi t. Okay,
Professor,
just a moment, just 1 second. There was also a factor 4 missing here, because I'm just taking so in the previous expression there was this plus the complex conjugate divided by 2. Is the yes?
So why do you miss the factor 4?
Yeah, because in the expression in the previous case, the perturbation was e to the I omega t plus e to the minus omega t times V divided by 2. This 2 squared is 4. Okay?
Yes. And also, actually, I have a question, and So we are talking about the resonance frequency or the natural frequency here, right? Which one denotes the resonance frequency? I mean, the omega ni or omega?
No. Just a moment. So when you say I'm considering a resonance frequency, you are just saying that you are choosing a frequency which is on resonance with the natural frequency. Okay? So this is the natural frequency. So the internal frequency, this is the external frequency. And the resonance condition is when these two match. And sometimes people say, okay, I'm just choosing a resonance condition or resonance frequency to mean that the external frequency matches the natural frequency. Okay?
Yes, thank you.
So why did I write in this way? So I write in this way because I want to analyze this function here. Okay, this function here has some nice property. So let's consider this. So it's a function which is sine square of tx divided by pi tx squared. Okay, right? Now let's see how it looks like. Now, when you go for x equals 0, okay? So in x equals 0, this is t over pi, okay? It will have a shape like this. So as a function of x, it will have a shape like this, or something like this. But the width, the width of the main thing goes like pi over t. Okay. So you see, and moreover, the integral over dx of this function of sine tx over pi tx squared is always equal to 1, between minus infinity to plus infinity. So you see that this function, so I just try to draw it. When t increases, so it will be like this, okay? It becomes sharper and higher, okay? Just a moment, see?
Sorry, Prof.
Yes.
Why is it always equal to 1?
You have to do it.
Oh, okay.
So just if you do it, then okay. But something you can see is the following, that so first of all, you can check that this does not depend on time. If you change, so this you can check. So for instance, if you go from tx, you just define the new variable, okay? Then you see that the integral of dy of this becomes sine y divided by 1 over pi y squared, okay?
Yes.
Okay, so this means that the integral does not depend on time. right?
Yes.
Then if you do it, turns out that is 1. But the important thing that I want to stress here, so
Sorry.
yeah.
You said earlier, and so if the T increases or something increases, that the peaks become higher, or?
Yeah, I'm just repeating this. So you see the peak scales like T over pi, okay? And so I just draw it like this, okay? So I just draw it. There are oscillation, okay? So let's say the peak is proportional to time. The width is proportional to 1 over time, okay? So this means that if times increases, let's take another color. The peak goes up and the width shrinks.
Oh, okay.
Okay.
Yes. Yes.
But then you see that if just consider this as a triangle, okay, just for the sake. Basically, you have the area under this peak scales like T times pi over T. It does not depend on time. Okay, so if you want to do it in a proper way, you just compute the integral and you see that the area, so the integral, sorry, is 1. Okay, so it turns out that actually this is one of the representation of the delta function, the Dirac delta function. So sine squared of Tx divided by pi Tx squared, when T goes to infinity, becomes delta function, delta of x. Okay. What does it mean? It means the following. That let's go back to, so I remove all this mess, okay? So that you can see the formula. This means that when T goes to infinity, or it becomes very large, then the probability on resonance to go from the state I to the state N is VNI squared divided by H bar square. I just keep the H bar times pi T. Okay. So now it is possible to define the rate, which is the rate to go from I to N, which is the probability per unit time. The probability per unit time is V N I square divided by H bar square sorry, here I forgot the delta function, which is important, omega n I minus omega divided by 2, okay? So I just write this, I have a pi, so I just write 2 pi. And delta of omega and I minus omega. If you write in terms of energies, just keeping the inside the delta function, the energies and not the frequency, I just get V and I squared divided by H bar delta H bar omega and I minus H bar omega. And I remind you that omega and I H bar is just E0 of n minus E0 of I. This goes under the name of Fermi golden rule. What does it mean? It means the following. So it means that the probability per unit time is given by the matrix elements squared. So you have to connect by perturbation two states. So selection rules should allow the transition between these two states. And the strength of the transition is given by the matrix element square. Now, the delta function is a kind of energy conservation. So since you're applying a perturbation for a sufficiently large time interval, then in a sense by the uncertainty principle, the energy is very well resolved. And the transition of the system is related to the fact that one photon with energy h bar omega has been absorbed, and as a result, the system, the quantum system, has gone from the state of energy E0I to the state E0N. Okay? Now, there is something which is very important that I will try to explain, but is not completely clear now, is the fact that when you talk about probabilities, then as we said before, perturbation theory puts a limit on the time over which this probability is valid when determined using perturbation theory. Now, and there are, I think you can derive this Fermi golden rule by several ways. When you compute the probability per unit time, what is really important is that the probability per unit time is small and is related to the fact that a single photon has been absorbed in this case. So Fermi golden rule has a very important application with in determining the fact that one could study, say, the dynamics of atoms in the presence of external radiation or external perturbation. So essentially, this expression is valid as long as one includes transition that are induced only by single photons. So the Fermi-Golden rule in this form is tells you that higher order processes like multi-photon absorption, emission, and so on and so forth are not included. I will come back to this point and we discuss, but I think for the moment, I think we can stop here. Do you have any question?
Yes, actually the energy conservation thing, and
yes,
yeah, basically you're trying to say that I mean, please correct me if I'm wrong. You said that since this is I mean, since this is a perturbation theory, and you derive this Fermi-Golden rule, and you actually just considering the single photon absorption, which is the lowest order. Or,
yes,
yeah.
yes,
And
exactly.
You can basically ignore any higher order like
yes,
multiple.
I'm ignoring it because
Yeah.
yes, I mean yes.
And then I don't really get the point where you about the energy conservation and the things you said before the energy.
So essentially, in order to if you have basically this describe a transition between real state, okay? The initial state, so the system is in a real so these are not virtual states. You go from an initial state, which is a real state, to a final state, which is a real state, over a very long time. So the longer is the time, the smaller is the possibility to have violation of energy conservation. Okay, it's just by uncertainty principle. Okay. Do you need my screen? Because
so because the time is really long, then
yeah.
you
So
have...
in fact, the delta appears when you take very long times. Okay. So this delta function appears in the limit delta to infinity.
And you're saying that it decreases the what error, or I mean
error? I did not talk about that.
I think that since T is really big, you can take this approach. I mean, if not, you cannot.
Yeah, so essentially, basically, if you apply, so let me say the following. Even if you apply, so okay, let me specify it this way. If you apply a frequency for a finite time, then this means that the frequency is not unique, is not perfectly resolved, because in order to you have a finite bandwidth. So in order to have really a single frequency hitting the system, then you have to apply for quite a long time. Okay. And so essentially you have this conservation of energy appears only in the long time behavior. I mean, longer, I mean, with the typical time scale of the atom. So it cannot be the edge, of course. So, I mean, the frequency should be very well resolved in order for the system to absorb it at that energy. Of course, I mean, you have absorption also when you are slightly detuned from the resonance frequency, right? So this is possible. So it's not that, so I mean, this Fermi-Golden rule is a result that is valid only in the long time behavior. But we know that if you apply a radiation which is slightly detuned for a resonance frequency, you still have some, which is related to the line width of the transition, okay? Hello?
Yes, yes.
More questions?
I have a question. Can you come back to the part before the part in periodic perturbation?
Sorry, I do not hear. May you come back to what?
Can you come back to the part that before the part periodic perturbation?
Which one?
Oh, maybe you deleted. Can you come back?
Yeah, but I don't know where should I go.
This the line that you have the underline.
Yeah.
When you write when you write sin t equal to 0 at the time.
This one?
Time, yeah. I
Yes.
don't understand why you wrote this thing, because I think you should put the perturb part.
No. This is a choice. I'm just assuming that the initially the system is prepared in phi 0 y.
Oh.
This is an assumption. Okay.
Yes. Okay. I lost this. Thank you.
So you may consider, so the initial time can be whatever. I wanted to consider, I'm supposed, for instance, this is I mean, it's a relevant situation in which you have that the perturbation is switched off on at a given time. So initially there is, it's like you have an atom which is in the ground state, okay?
Yeah.
So you shine light. So at a given time, perturbation is switched on. So the system was in a given eigenstate, in the ground state, for example, then just light arrives and there are transitions, okay? And this is a situation in which the initial wave function is an eigenstate of the unperturbed Hamiltonian, and then you study the transition to other states, okay?
Yes, thank you.
More questions? Okay, so I will see you Thursday, okay? And please remember, if there are things you want to describe, you want to discuss, then probably in group of 1, maximum 2, we can meet on the terrace with some enormous distance between us, but we can discuss, okay? So just send me an email if you need to discuss about specific, and we'll find a way to do it, okay?
Okay.
We cannot gather all together, okay?
Yes,
this is not possible. We just group in very small subgroups, okay? Bye-bye.
Goodbye.
Bye-bye. Bye.